Hello again, Conceptual Physics. Here's another example of a calculation using Pivot Interactives to measure speeds of what I'm going to call a glider explosion. So here's how this one works. We have two of these masses that are, I don't know if you can tell on the inside there, but they have this teeny little spring that is kind of smushed and waiting to explode. And then the student comes along and cuts that ribbon so that, watch what happens. Now, what's the physics here? Well, let's talk about basic physics. Newton's third law, action, reaction, impulse, momentum, all of our good friends. What we know is that the force of the explosion is an action-reaction pair. So the force from the gold cart on the blue cart is the same as the force from the blue cart on the gold cart. Now, the same force, different masses. I think we can say that the second law, Newton's second law, would show us that the gold one should accelerate more, which it does. Now, the impulse momentum equation, on the other hand, says that the impulses are equal and opposite, so the changes in momentum are equal and opposite, which means that after the collision, these two things, believe it or not, carry away the same momentum. Well, how do we know? Because momentum is a conserved quantity. How much momentum is in this system right now? Nothing's moving. There's zero total momentum. So after the explosion happens, there has got to be zero total momentum. Total momentum is the total of the two together where direction is taken into account. In other words, the leftwards momentum of the gold cart has to be equal and opposite to the rightwards momentum of the blue cart. So how could that possibly be? Well, the little guy's going faster, the big guy's going slower. Let's do the calculation and find out. The total momentum beforehand should be zero. So I'm going to bring up a little pen here. Let's see. Oh, that's not a pen. That's a pen. I'm going to bring up a pen. The total momentum in the system before is equal to zero because nothing's moving. The total momentum in the system afterwards is going to be equal to the negative of the gold cart, or yellow cart, plus the momentum, the positive momentum of the blue cart. Now, if two numbers add to zero, they've got to be the same number, but opposite in sign. So let me bring up my tools. I've got my frame clock. I've got my ruler. I'm going to say, I'm going to move this ahead to, as soon as they stop touching, ready, set, go. Okay. See how the spring is released? I'm going to bring my 30 centimeter mark just to the, stop that. I'm going to bring my 30 centimeter mark just to the right of my cart. And I'm going to reset my frame clock here. And I'm going to say, okay, well, this cart should go, I don't know, let's see. Whoa, that was quick. So I go at frame equals 0, I go forward in time to, let's say, frame equal, I don't know, frame 12. Well, that's not quite easy to measure distance, so let's see. I've gone from 30 centimeters to 20 centimeters, roughly. So that is a distance of, for the cart, the gold cart, negative 10 centimeters divided by a time elapsed of 0.1583 seconds. Okay, let me grab my calculator. I've got 10 divided by 0.1583, and I see that this cart is going 63.2 centimeters per second. And this cart has a mass, let's see, the mass on the left, I can see it right on the video, it says 140 grams. So I'm going to take that number and I'm going to multiply it by 140. Actually, why don't I use 0.14 kilograms just to, I don't know, get a smaller number. And then the mass times the velocity is, so 0.14 kilograms times 63.2 centimeters per second. My calculations indicate that there is 8.84 kilograms, centimeters per second, negative units of momentum from that yellow or gold cart. So I'm predicting that there's exactly that same amount of positive momentum from the blue cart? Let's find out. Take my ruler, bring it over here. I'm going to rewind. So we've got just, okay, there's collision right there. I'm going to say put the left edge of my blue cart at the 20. I'm going to reset my frame counter. I'm going to go, let's see, from frame 0 to, let's see, I went to 30 centimeters. So the blue cart went from 20 to 30 in 77 frames. So what would that mean? So I have a distance of 10 centimeters and a time of 0.6417 seconds. That, according to my calculations, is, please be patient, 6417, 2.18 centimeters per second. It's going a lot slower. Why? Because it's heavier and it's got to have the same momentum as the other guy. So this blue cart has a momentum of 0.56 kilograms mass times velocity of 2.18. That, let's see, when I do out that calculation, I get 8.72, positive 8.72. Now, let's take a look here. Total momentum after the explosion is negative 8.84 kilograms centimeters per second plus positive 8.72. That gives me a total momentum of negative 0.12. So you're saying, Mr. Fumato, the total momentum in the system afterwards is not zero. Clearly momentum is not, so what do you think I'm going to say? I'm going to say it's pretty close, and also on a percentage basis, right? We always think about percent differences in physics. On a percentage basis, I am definitely within 10% of the total momentum of one of those carts, right? Taking roughly 10 units away, and I'm off by 0.1. So that's within 10%, and I'm not being particularly careful with my measurements here. So I would say that this is pretty good evidence that momentum is conserved. The equation that I used was 0 is equal to m1v1 plus m2v2. Okay, that's the general idea. Have a good afternoon.